All right, hello and welcome. This is the first lecture in the lecture series on crystalline silicon solar cells, so hopefully you clicked on the right video. My name is Edward LeBeau. I'm a student here at Arizona State University. I'm studying electrical engineering, and God willing, I'll graduate in May of this year, 2017, and go on to do great things, starting with grad school. In this lecture series, we're going to look into all these bullets here. First, we'll do an introduction. We'll talk about the terawatt challenge. That's how much energy does the world need and what role does solar energy play in that. Then we'll look into the operation of silicon solar cells. So how does a solar cell operate? Light shines, sun happens, energy comes out. What's going on, right? What's going on inside of that? How does light become electricity? And then after that, we'll look into the manufacturing of silicon solar cells. How are they built? What's the process to building a solar cell? We'll look into that in two parts. One is, what is the industry standard of manufacturing a solar cell? And then what's a lab standard of manufacturing a solar cell? Especially, what's the lab standard at ASU's Solar Power Lab? And then after that, we'll look into the characterization of silicon solar cells. So what is characterization? Characterization is figuring out if you made a useful solar cell, if that's a PV cell or a solar thermal or anything like that. Characterization is really how you figure out what does it do and how does it do it. So you'll figure out if you made a glorified paperweight or a useful solar cell, and hopefully you'll also know if I made a glorified paperweight, how do I not do that again? How do I actually make a great solar cell? And characterization figures all those things out. And then after that, we'll look into the economic impact of solar. What role does solar really play in the economy, and if it's really a viable option? So let's dive into the introduction on the terawatt challenge. So real quick, a lot of people dive in and tell you terawatt, kilowatt, terawatt hour, terawatt year per year, all these weird units. And I'd like to clear that up before we jump in. So basic understanding, a kilowatt hour is a measurement of energy, which is like a joule. A joule is a measurement of energy. You can get hit with 1 joule of energy. So a kilowatt hour is 1 kilowatt, so 1,000 joules sustained for an hour. Or you can think of it as 60,000 joules of energy, right? That's a measurement of energy. A kilowatt, right? No hour. A kilowatt is a measurement of power, which is a joule per second. So 1,000 kilowatts is 1,000 joules per second. Terawatt, quite simply, is 10 to the 8 kilowatts, or 10 to the 12 watts, right? So real simple, just think of it like this. Kilowatt hour, energy, joule, kilowatt, joule per second, right? So that's a kilowatt, or power, is how much energy you could make per unit time. Kilowatt hour, or energy, is joules, okay? So let's keep that straight. We don't want to get those confused. So now let's dive in. How much power? So how much power does the U.S. use per se? So the U.S. uses about 3.3 terawatts per year. Terawatt years per year is the way to look at this. So terawatt year, like a kilowatt hour, per year. So every year we use 3.3 terawatt years of energy, which is a massive amount. So the world uses 17.5 terawatt years every year, and the world, with reduced poverty, if poverty were reduced, would put that number up at 60. So there's a massive, massive amount of energy demand, a huge amount of energy demand, and it's only going up. Without reduced poverty, which poverty will be reduced, the estimate is 24 terawatt years of energy required every year by 2030. So there's a massive energy requirement, and it's only going up. So as this energy requirement goes up, we have to figure out some sort of lasting solution. What's our lasting solution? So the world demands all of this, all this energy, and it's going to keep demanding more. How do we satisfy that need reliably and sustainably? So let's look at this. Okay, present energy demand, 17 terawatt years every year. Okay, let's look into wind. Wind, the amount of wind on the earth is about 50 terawatt years every year. So annually we can get about 50 terawatt years of energy from wind. So that's a reasonable thought, but then realize that that's if we could collect 100% efficiency of the wind, right? We could 100% convert 100% of the energy in the wind to electricity, which we can't do. There is no such thing as a 100% efficient process, especially in energy conversion. So natural gas is 215 terawatt years of energy total. That is the entire amount of energy from natural gas that exists worldwide. That isn't an annual, that isn't some sort of yearly allowance or anything like that. That's total. So remember, now we're getting into the non-sustainable solution. So what's our short term? Natural gas does provide a viable short-term solution, right? 17 terawatt years every year. Well, okay, we have 215 terawatt years of natural gas. Do the math. We could run off solely natural gas for a good chunk of time. And then there's also coal, which is another large currently used energy solution. Coal is about 900 terawatt years total. So again, do your math. You last even longer with coal than you will with natural gas. But remember, the loss with coal and natural gas is, one, environmental damage and all that. But the big thing is it isn't going to last. It will run out inevitably. So it isn't a sustainable, lasting solution. Solar, its annual amount of energy that solar hits the surface of the earth is 23,000 terawatt years. Every year, 23,000 terawatt years. So what does that equate to? You're probably wondering, what is that, how do we get that? What does that equal to be powering my home or the world? Basically, in a few hours, if you could harvest all the energy hitting the surface of the earth from the sun in a few hours, you would have enough energy to power the world. So just a mere few hours. So it looks very clear from here. The most viable solution is solar, right? And hopefully you're beginning to think that because there's so much available. It is a massive amount of energy. Now, to harness it is another question, and there's many pursuits to figure out how to harness that energy and collect it well and effectively. Because solar not only is a massive amount of energy, it also provides great incentives for national security, right? You don't have to ship solar energy in and out. You build a solar cell wherever the sun shines, and it all works out. It isn't this big energy ball in a real tight space, right? With coal or natural gas or even nuclear, you have all this energy in this tight area where if something goes wrong, you get a real big explosion. That's another big national security risk and all that. So solar provides a lot of good options. It also is very scalable, which is a very useful thing you can do. And by scalable, I mean you can go from small residential to large, huge, big scale power plants. So it's very scalable, which also helps for it being more readily available to be built. So if you look at this, the world is beginning to realize this as well. The first half of 2015 to the first half of 2016, there was a 45% growth in the photovoltaic market, which is over 4 gigawatts of energy, of power. So that's a massive amount. And that's about enough electricity to power 6.2 million homes, right? So quite a few. And solar prices dropped 18% from Q2 2015 to Q2 2016, which is a huge price drop. And it was across all market segments of solar energy. So there's a massive amount of price drop in 1 year, which is none of the other energies are dropping in price that quickly. So it's becoming a much more viable option. Now, if you look at this graph, there's that red line with the dots on it is the price per watt of solar energy over the years. So if you look at it, a massive downward trend from 2009 to 2016, and it's getting down to about $2 a watt. So a big thing to know, if you're $1 a watt, you can compete in the free market for electricity. You are more than good enough to compete with anyone. So right now it's $2 a watt. It's a little difficult to compete, but it is rapidly dropping and is continuing to drop. And once it becomes about $1 a watt, it will need no outside incentive or anything like that. Just the mere price will be enough for solar to succeed very readily in the current energy market. And if you look at this, there's not only is industry or the grand, large world beginning to realize to build solar power plants, also on residentially, people are building a lot of solar. If you look at it from 2006 to 2016, there's a massive upward trend in solar installations. If you look at that blue line, in 2016 alone, there was somewhere from 2,500 to 3,000 PV installations. And on non-residential PV, so like power plants, things like that, there's somewhere between 1,000 and 1,500. So that's a massive amount of growth of solar installations every year. And that's, if you look at it, 2016 is about 2 times the growth of 2015. So massive growth rate. The solar industry is growing rapidly, and there's about 13.9 gigawatts of capacity currently in existence of solar energy. So very large, growing very rapidly, becoming a very viable solution. So as you look at this world of solar, you'll hear high efficiency all the time. That's everyone's first question. They want to know how efficient it is. And it is important. It's very prestigious to have a very high efficient cell. It's an academic pursuit in many ways. Like if you had a 40% efficient cell, 50% efficient cell, you would be very famous, and the world would very much respect your research and all those things. But there is something more than just the pride to it. It does drop the levelized cost of PV energy as the cell becomes more efficient and the system becomes more efficient. So there is some importance to it. But what's the most important thing? The most important thing is your price per watt. You want to be $1 a watt. So efficiency aside, price per watt is what you're looking for. If you had a 40% efficient cell and it costed you $10 a watt, you're not going anywhere. Or $50 a watt, you're not going anywhere. But if you had a 12% efficient cell and it costed you 25 cents a watt, you'll be very competitive. Now you do want to have a higher efficiency. That way the area consumed by your PV power plant or your panels or whatever isn't massive. You know, if you had 1% efficient cells, you would need tons and tons of land to put these solar cells and solar modules in. So you do want a good level of efficiency, but the real thing you're looking for is a low price per watt. So that's all for this lecture. Hopefully you're convinced that solar energy is a viable option just by the raw amount of energy there is, the massive amount of energy available. And we're going to be continuing our lecture series, so hopefully I'll be seeing you soon. Thanks. Have a good